here's the basic idea about Leibnitz's notation for calculus. We're thinking of the derivative as kind of the limit as the change in x goes to 0 when we have some change in f divided by some change in x, right? The outputs are changing and the inputs are changing, and when we look at that ratio and we shrink the interval over which those inputs are changing down to nothing, that's when the magic of the derivative happens. Right? So at that instant, at this infinitesimally small instant, instead of talking about deltas, at this infinitesimal level, we start talking about d's. So we use this notation, d over dx. And it might be parenthetical, right? So this means take the derivative of f of x. We also saw things like delta y over delta x. So we might see this notation, dy over dx. So we see it in both contexts. This is the derivative of y with respect to x. This is the derivative with respect to x of f. Okay? So it can be an operator that is operating on something, right? This is a process that we have to undergo, right? This is instructions. It tells us take the limit as the change in this function of the ratio of the change of this function over the change in x, right? X. And shrink that change, this change, to 0. And what pops out of it, right? This is instructions to do this whole limit business. It turns out, though, that thinking about the derivative in these terms, the terms of a fraction, can be very, very useful when we think about other operations that we want to do with derivatives. So we will find times where thinking about the derivative as like this fraction is helpful. And we'll see this notation often. Another great use for this notation is that sometimes we want to change what we're taking the derivative with respect to. Okay? So say, for instance, we have something like this. P is pressure. Well, P might depend on a variety of things, right? There might be a lot of things that are changing inside of a balloon if we were considering about balloons, right? So we could be talking about volume. If the volume changes inside of a balloon, then the pressure inside of that balloon will also change. Temperature. If we let T be temperature. If the temperature of the gas inside of a balloon changes, then the pressure inside of the balloon will also change. The idea is that, like, when you heat it, that the air gets all excited, right? And so it expands. And at cooler temperatures, it's less active, and so it'll shrink back. You'll have less pressure. If you ever take a helium balloon and you stick it in the fridge or the freezer or something like that, you find that it shrinks up. And then if you took it out and left it at room temperature, it would gradually kind of re-inflate. So that's something fun if you're ever spending a weekend with some kid that likes balloons. Right? So the pressure is going to change, but it'll change if the volume changes, and it'll also change if the temperature changes. So if all of these things are changing at once, we might be interested in something like this, the derivative of pressure as volume changes, dP dV. Right? So you give me a volume, and I will tell you how fast the pressure was changing as the volume changed. But we could also have dP dt, right? At a particular temperature, how fast is the pressure changing as the temperature is changing? Right? And you'll notice that the units for these are also going to be different. This might be in something like pascals per cubic meter, and this might be in pascals per degree Celsius. Because here, temperature is changing, and as temperature changes, I want to know how fast the pressure is changing. Whereas over here on the left, volume is changing, and as the volume changes, I want to know what's happening to pressure. So Leibniz notation is really useful here. If I said P prime, if I use the prime notation, I don't know what's changing. Pressure, certainly, but is P changing with respect to volume, with respect to temperature? The Leibniz notation is more exact than that. Where the prime notation has it for sure over the Leibniz notation, though, is ease of writing, right? P prime is a lot easier to write. Also saying something like P prime of 10, this is telling me I'm interested in the rate that P is changing when the input is 10. That's very nice. The way that we write it in Leibniz notation is a little bit messier. Right? We would write dp dt, and then I would use this bar afterward, and then at the bottom of the bar, I'm going to tell you where I'm talking about. So this says, evaluate this expression, right? I want to know the derivative, but I want to know it when t is 10. So this is a little bit cleaner, I think, to look at, a little bit easier to interpret what the input is. And here I've got this nasty bar with a little subscript. It's less nice to look at. It takes a little bit more time to write. I don't know. And again, if mathematicians are anything, they are lazy. But remember, right? Leibniz notation, it's got these fractional forms. And while the derivative isn't a fraction, right, it's the limit of a ratio as the denominator of that ratio shrinks to nothing. Right? And it's a very particular ratio. Sometimes we might be able to treat it like a fraction and get away with it. And so that's one of the reasons why I think Leibniz notation is great. And then the other is that it gives you a lot more specificity as to what you're taking the derivative with respect to. So we will be using this notation interchangeably with the prime notation, kind of like going forward. So expect to see both. Feel free to use both.